In the last class, we discussed about the rotational vibration spectrum. And in this class, we will start with the breakdown of von Oppenheimer. Von So, according to this von Oppenheimer approximation, we treat the vibration and rotation independently. So, the last section also, we considered for a molecule, the vibration and rotation happens independently. So that the energy we have taken as separately, one is corresponding to rotational energy, second one is for vibrational rotation. So that is the Oppenheimer, von Oppenheimer approximation, where we will treat the vibration and rotation individually, and we take all the values associated with vibrations and rotations independently. But in reality, that is not the case. When we will be having a molecular rotation, the molecule will vibrate at least 10 raised to 3 times within a single rotation. Okay. So the vibration, the first point is vibration and rotation, which are not independent in reality. Okay. That is vibration and rotation are not independent. Okay, and this statement is the breakdown of von Oppenheimer approximation, because von Oppenheimer approximation says that the vibration and rotations can be taken as independently, but in reality these two are not independent. These two are dependent on each other, and this particular scenario is called as breakdown of Oppenheimer approximation. Von Oppenheimer. So this is the first point, that is the vibration motion and rotational motion of the molecule, which are not independent. Okay, so for any molecule, if you consider a molecule that will vibrate at least 10 to the power 3 times, molecule vibrate 10 to the power 3 times in a single rotation. So what that means, hence bond length as well as B parameter, okay, that is the rotational constant, changes continuously during so in these rotations, first this bond length will change because there is vibration happening. So for example, if you consider a molecule, linear molecule, let's say this is xy. So if this molecule is rotating, let's say about this axis, this is just an example. So consider this as the rotation axis. So if this molecule is rotating about this axis like this, okay. So if this molecule xy which is rotating like this, and then according to this Born-Oppenheimer approximation, this rotation can be treated independently from the vibration, but that is not the reality. Along with this rotation, vibration also happens. So in each time, this, for example, in this rotation, in the very next moment, the bond length will increase a little bit because of the, for example, stretching vibration. And in the next moment also, bond length may increase a little bit. Okay. Then reaches here maybe this. Okay. So like this, it will change. So the bond length will change. Okay. So each time this bond length will change. This is y, this is x, until it comes back to its original position. Okay. So each time it will vibrate. It will vibrate means it will be having a change in bond length from its original bond length. Okay. Then within this complete rotation, when it completes its rotation, its bond length will become the same as the initial bond. Okay. So in each time, within a single rotation, there will be at least 10 raised to 3 times vibration will happen within a single rotation. So because of these vibrations, the bond length of this molecule will change. Hence, since the bond length is going to change within a single rotation, this bond length is associated with the B value, rotational constant, because your B is proportional to 1 by mu, and mu is proportional to r square. Sorry, this is I. This one depends on I, moment of inertia, and that I is proportional to r square. Mu r square will come here. So if your bond length is going to change, your B parameter is going to change. So within a single rotation, as we discussed before, within a single rotation, there will be vibration of molecule, and within that one single rotation, there will be 10 raised to 3 times the molecule will be vibrating. So in each of those vibration, this bond length will change. Okay? In each of this vibration, that bond length will change, and because of that, your rotational constant is going to change. So that is the breakdown of Oppenheimer approximation, because we cannot treat the vibration and rotations independently, as these two happen simultaneously within a molecule. Okay? So this B parameter depends on 1 by r square, as you can see here. And when your r is going to change, bond length is going to change, the P parameter also change. So an approximate equation that is given by like this. So we can connect these two uh, can be connected or related. These two means vibrations and rotation. Okay? Vibration and rotation can be related with an equation. This is an approximate equation, which will give you almost same value. So with an equation, that equation is VV equal to VE minus alpha times V plus R. So BV, where BV equal to BV, you can say BV is rotational constant of vibrational level V. Rotational constant of vibrational level V, and BE is the equilibrium value of V. Equilibrium value of V, and alpha is a small positive constant for each molecule. So for each molecule. So BV is the rotational constant of vibrational level V, which means that if your molecule is at this position, okay, and your molecule can have another position like this. Okay. So in this case, we have R value, that is the bond length, which is, let's say, this bond length is R1. This one is R1. And let's say this bond length, okay, this is R2. Then obviously R2 is greater than R1, right? This bond length will be larger as compared to this one, and your initial bond length is R. So R1 is greater than R2 is greater than R1 greater than R. So when you are considering R2, which will be associated with one particular vibrational level, let's say V2, and this R1 will be associated with V1, and this R will be associated with V. Okay. So in each of these, for each of these bond length, we have different vibrational energy level, because when your bond length is different, your vibration is different. Means that it is, if you are considering stretching, your stretching will be more when your bond length is larger. So the vibrational energy will be larger in that. Okay. So in this case, R2, you will be having a different vibrational quantum number or energy level as compared to R1. So we can denote this vibrational level as V1, V, V1, V2. V, V1, V2. So in associated with this vibration levels, we will be having rotations, because when you consider this particular vibration level, we have a rotation like this. Okay. And when you are considering this R2 bond length, we will be having rotation with this much of bond length. So in each case, we have different rotational constants, because our bond length is different. When your bond length is different, you can obviously see from this equation that when your R is different, your B is going to be different. Okay. So for each of these different bond length, so different R value means we have different vibrational energy levels, and associated with that, we will be having different B value. That B value we can denote by BV, that is the rotational constant of vibrational level. rotational constant of, we have different rotational constant. And B is the equilibrium value of these B values that is associated with the different vibrational energy levels. And alpha is a small positive constant which is associated with the molecule. So for each molecule, we will be having different value for this alpha. Okay, so this is the equation which connects the vibrational and rotational uh, motion of this particular molecule. And if you restrict our discussion for a transition from v equal to 0 to v equal to 1 only, and take the b value as v0 and v1. So we are considering the transition. If we restrict transition for our discussion, for transition v equal to 0 to v equal to 1 only. So we are considering only this transition. Okay. Then and take b values as b0 and b1 for v equal to 0 and v equal to 1 with v0 greater than v1. Okay, so if you restrict our discussion to this transition only, that is from v0 to v1, and if you are considering the b value associated with these two states, that is v equal to 0 and v equal to 1, as b0 and b1. Okay? So b0 is the rotational constant associated with the vibrational energy v equal to 0. Okay? Vibrational state v equal to 0, and b1 is the rotational constant associated with the vibrational state v equal to 1. So if you are considering like that, then b0 will be larger than b1 because vibration v equal to 0 will be having lower energy, v equal to 1 will be having higher energy, which means that v equal to 0 will be having smaller bond length, smaller r value. This you can see from here also, that if you are considering this particular level for V, so the bond length will be smaller as compared to V equal to 1 case. Okay. If you are going for any higher level, we will be having larger bond length. So when larger bond length means we will be having higher vibrational energy. Okay. Larger bond length, we will be having higher vibrational energy. But when you are considering, so this case we have higher R value. So when your R is larger, your B will be smaller, okay, because B is inversely proportional to R. So V equal to 0 will be having smaller R value. So B0 will be larger than B1 because B0 is B is inversely proportional to R. So when you are having smaller R value, corresponding B will be larger. So if you are considering this particular transition, the energy difference delta epsilon will be equal to epsilon J dash comma V, this case it is V equal to 1, minus epsilon J double dash comma V equal to 0. So this J double dash is the rotational quantum number associated with at V equal to 0 energy level, that is vibrational energy level V equal to 0. And J dash is the rotational quantum number at which V equal to 1, vibrational level. So if you take the difference between these two energy levels in the universe, then it will come as omega 0 bar plus will be b1 times j dash into j dash plus 1 minus b0 into j double dash j double dash plus 1. This is simple. This one we already know. Omega 0 bar is the vibrational band at the central band that is associated with omega e bar into 1 minus 2 xc, that is equal to omega 0 omega e bar into 1 minus 2 xc. So this is the total vibration energy, okay, difference in that vibration energy. And this one is the rotational energy associated with the first mean excited state, that is v equal to 1 state, that is b1 into j dash into j dash plus 1, and v0 into j double dash into j double dash plus 1 is the rotational energy associated with this v equal to 0. Okay, so this is the vibrational energy difference that is constant, that will be there, and with that we have this rotational energy level differences. Okay, this is the excited energy level minus ground state energy. So that is the so omega 0 bar is nothing but omega 0 bar is omega e bar into 1 minus 2 x. This is this we already know. That's why we are not calculating. If you are considering v equal to 1 level and v equal to 0 level, if you take the difference between these two level vibrational energies, then we will get this expression omega 0 bar. Okay. That is omega e bar into 1 minus 2 x will be the difference between v equal to 1 level and v equal to 0. If you take that difference, that you can do by considering that v plus half into that energy equation that we already discussed in the vibrational spectra. So if you take that equation for v equal to 1 and v equal to 0 cases along with xc, okay, then we'll get this particular equation. This we already did in several cases. So this is the difference between the vibrational energies v equal to 1, vibrational state v equal to 1 and v equal to 0. If you are calculating that, you'll get like this. And that is constant omega 0 bar. Then we have that rotational energy difference. That is first case we have v1 into j dash plus 1. That is the energy in terms of wave number centimeter inverse. And this is the energy corresponding to the ground state, that is v equal to 0 state rotation. Okay. So if you take this difference, then we'll get the difference between the rotational energy. So this is the equation corresponding to this particular transition v equal to 0 to v equal to 1 when we are considering rotation as well as vibration simultaneously. Okay. Now we have two cases in this case, in this particular scenario. Now we have two cases. First case, that is delta j equal to plus or minus 1. So if we consider delta j equal to plus 1, what will happen? The first case, delta j equal to plus 1. If delta j equal to plus 1, which means that j dash equal to j double dash plus 1. What is this delta j equal to plus 1? Delta j equal to plus 1 means your transition is from the ground state to the excited state. Okay. So that's why you are putting j dash equal to j double dash plus 1. So j double dash is your ground state or the lower state. So from that, you have to move plus 1. Okay. Then you will get into this this j dash. So j dash equal to j double dash plus 1. That is this transition. And also delta j equal to, we are considering, So j double dash plus 1. So that will give delta epsilon that will be equal to, what will happen to this? Omega 0 bar, omega 0 bar plus, I'm not going to discuss all those values here, b1 plus b0 into j double dash. So you just substitute what this j dash equal to j double dash plus 1 in this equation. Okay. So I will so substitute j dash equal to j double dash plus 1 in 1, then you will get this particular. So you substitute j dash equal to j double dash plus 1 in this position, then we will get like this. So b1 plus b0 into j double dash plus 1 plus b1 minus b0 into j double dash plus 1 square. So in this case, when delta j equal to plus 1, all the j values will be in j double prime. Okay, if you remember, because we are substituting for j dash in this particular equation. So j dash will be replaced with j double dash plus 1, and we will be having this kind of. Similarly, if you consider second case, that is delta j equal to minus 1, when delta j equal to minus 1, we have j double prime equal to j dash plus 1, or j dash equal to j double dash minus 1 in this particular. So the transition is from the higher state. Okay, from 1 to 0 we have to. Then only we will get delta j equal to minus 1. So j double prime will be, so in this case j double prime will be replaced with j dash plus 1 in this equation 1. Okay, so all the j terms will be j prime in this expression. So this will give you delta epsilon equal to omega 0 bar. Very small change will be there. So b1, this will be minus omega 0 bar minus b1 plus b0 into j prime plus 1. Again, this plus b1 minus b0 into j prime plus 1. So these are in centimeter inverse. So this is not a big task. You just substitute j dash equal to j double prime in this particular equation, in this equation 1. Then we will get this expression. And if you substitute j double prime equal to j dash plus 1, then you will get everything in j prime. That is the second equation. Okay. So that you will get by substituting these values in that. So these are the two equations corresponding to these two different transition, delta j equal to plus 1 and delta j equal to minus 1. Okay. Now, if you are considering this together, okay, together we can write it as delta epsilon equal to, this will be we can take it as in mu bar p comma r. This will be equal to, okay, this is also equal to mu r, because we are over r, because we are considering delta j equal to plus 1. Plus 1 is associated with the r branch. Okay, this is p bar, is associated with p branch. This we already discussed in the last class. So mu bar p comma r will be equal to omega 0 bar minus. So here we will take this as plus and b1 plus b0 this times m plus b1 minus b0 again m square. So this much of centimeter. So this is together. We are combining these two equations into a single equation. This equation where m can take values as we know. M can take values plus or minus 1, plus or minus 2, plus or minus 3. M value associated with the j prime plus 1 and j double prime plus 1. And when delta j equal to plus 1, it is associated with the j double prime plus 1. So m can take values j double prime plus 1 when delta j is equal to plus 1. And also this is positive. Okay. So positive value will be positive. And m value will be equal to j double prime, sorry, j prime plus 1 and negative when delta j equal to. Then it will come, this negative will come in the second. We consider m as negative. So there it will come minus j prime plus 1. And in this case, it will not affect because when you are taking m as negative and taking square of the negative, it will not affect. Second. Okay, so this is the expression. This is the expression for the transitions or the wave number corresponding to the vibration and the rotation when it happens simultaneously. Both happen simultaneously. And in this case, since B1 is always less than B0. We already discussed B0 is greater than B1 because R will be smaller for the ground state vibrational level. So B0 will be larger in that case. So B0, so B1 is less than B0. So the second term, third term last. The last term in equation 2 will be always negative. So when you are considering B1 and B0, B1 is smaller than B0. So this term, this last term will become, this last term, always this last term B1 minus B0 m square, that will be always negative. Okay. That term will be always negative. So what happens when you are considering that separation between lines in R branch? Okay, so you can see from here. For the case of R branch, we have here. For R branch, we have here positive, and this term always will be negative because B1 minus B0 is negative. So this term here we will get a negative term. Okay. So when you are considering the separation between the between each of the line in the R branch, that will be reduced in each case because when you are having a minus sign here, so it will be always subtracted from this quantity. Okay, so the separation between lines in R branch will be always reduced. But when you're considering the P branch, we already have a negative sign here for P branch, and we have V1 minus V0. This term that will become negative because P1 is less than V0. So this is again will become negative. So in this case, we will be having an effective increase in the suppression. Okay, so the suppression will get increased in P branch. So if you're okay, so because of this fact that B1 is less than B0, the suppression in P branch will always get increased. So if you consider that from the center line omega 0 bar and minus some large quantity will come with the distance. In each time it will be getting increased because we have a minus here and we also have a minus here. So this quantity will be increased. So we have to add those two terms together, and that has to be subtracted from the central band. Okay. So the separation between the lines in the P branch will get increased this time. But when you are considering this R branch, we have this central band frequency omega 0 bar, and we have a plus sign here and a negative sign. So in each time, this second term has to be subtracted from this term. So in each time, the separation between the lines will get reduced. So that we already shown in the figure in the case of the carbon monoxide, that for R branch we'll be having the separation that will be getting reduced in each time. So like this, so that the separation is getting reduced like this. But in the P branch, P side, we have the separation that is will be increasing. So this side we will be having an increase. Okay, so this we already discussed in the last class for the carbon monoxide. We have this diagram, and this is your R. This is so for P, as you move this side, the suppression will get done. And here we will be having decreasing effect of suppression. Or if the wave number is increasing, so the wave number is increasing in this side, this side. So the suppression of these lines will get reduced. So that's all about the breakdown of von Oppenheimer approximation. Now we will discuss the vibration of polyatomic molecule. So far we discussed about the vibration of the diatomic molecule. Now we will discuss about the vibration consider a molecule with n atoms. Consider a molecule with n atoms. So if you are having n atoms, each of these atoms can be specified by using three coordinates. If you are using Cartesian coordinate, it will be x, y, z. And by using these three coordinates, we can specify each of these atoms' position, so that if you are having n such atoms, then the total degree of freedom associated with those n atoms will be 3n. Okay, so the molecule is now having 3n degree of freedom. Then if you are considering once that bond length and bond angles are fixed, the atoms itself cannot move within the molecule. Okay, in that case we can have only that the translational motion of the molecule. Atoms cannot move because once that bond length and bond angles are fixed, then only the translational motion is possible for the molecule. Once the bond length is fixed, this line, the bond length and bond angles are fixed, then the molecule can move as a whole, which means that only the translational motion is possible. And this requires 3 degrees of freedom. This where this requires 3 degrees of freedom. I will write it as TOF. So 3 degrees of freedom from 3n degree of freedom of that molecule. That implies, so total degree of freedom will become 3 equal to 3n minus. So from that 3n total degree of freedom, 3 degrees of freedom will be taken by this translation. And another motion that is possible is that the rotational motion. Okay, another 3 degree of freedom also required for rotational motion. This also you might have studied in classical mechanics. So if you are considering a rigid body like this, and if you are having that x, y, z axes. So for example, this is the center of gravity. So in order to specify the translational motion, we need the center of gravity. We have to specify the center of gravity. So the center of gravity will be x, y, z, and this center of gravity will be a single point for a single molecule. Okay, and this can be specified. So what is x position, y position, and z position for this particular center of gravity point can be specified for the translational motion. Okay, so when the molecule move as a whole, we have to consider the center of gravity point in order to represent the molecule. Okay? So if you are considering an atom, that can be considered as a point in the Cartesian coordinate. Okay? But when you are considering the molecule as a whole, it is not a point. So we have to specify a point, and that point will be the center of gravity of that molecule. If you are considering any rigid body, the center of gravity of that particular rigid body will be the point where we represent that in a coordinate system. Okay, so for this particular molecule, we have to consider the center of gravity point, and that point we have to specify when you are specifying the molecule as a whole. So that these 3 degrees of freedom are possible, that this molecule as a whole can move in x direction, y direction. Another possibility is that this molecule, if you are fixing the center of gravity, this molecule can rotate in 3 different axes. One along this x-axis. Okay, this x-axis can change to x dash with an angle. Okay, this angle that can be represented as theta. And also angle will be changing to that rotation. In that case, we have to represent the center of gravity. So along with this translation motion, we can also have the rotation of this rigid body or this molecule, and that x can change to this x dash, y can change to y dash, and z axis can change to this z dash position, and with the angle of that this can be represented as phi, and this is psi. So that is not a matter, but importance is that there can be 3 degrees of freedom associated with the rotation of molecule also. So that is these 3 degrees of freedom. So then we have the total degrees of freedom. Now the total degree of freedom will be equal to 3n minus 6, because 3 degrees of freedom is already taken for translational motion. 3 degree of freedom is taken for rotational motion. So total degree of freedom is 3n, and minus this 6 degree of 6 degree of freedom. So this will be the degrees of freedom associated with total degrees of freedom associated with the nonlinear molecule. This is for nonlinear molecule. Why it is different for linear molecule? For linear molecule, rotation about the axis that is not possible. Okay, for example, if you are considering the carbon dioxide molecule, consider carbon dioxide molecule. This is a linear molecule, so it can rotate like this. It can rotate this in the plane of this paper, this screen, and also it can rotate into and out of the plane of the paper like this. It can go like this. This is also possible. This kind of rotation is possible. Also, this rotation is also possible. That is in the screen as well as into and out of the plane, out of the screen. These two are possible. This particular rotation is not possible. About the axis, the rotation is not possible. Linear mode. Okay, so there will not be 3 degrees of freedom associated with rotation. There will be only 2 kind of rotation possible. So only 2 degrees of freedom for rotation is possible in case of linear mode. So this about the axis is not possible. For example, if you consider another molecule like this, nonlinear molecule, let's say this is x, y, z. So in this case, it can rotate in this plane. It can rotate into and out of the plane. Okay, out of the plane is possible. Also, it can rotate about this axis, because when it rotates this x, this z and y, that these 2 atoms will change its position. Okay, so this kind of rotation also makes changes in the energy level. But in the case of carbon monoxide or any linear molecules we consider, about this axis, if you rotate the molecule, there will not be any change. Okay, so about that axis, we will not be having any kind of rotation, or that kind of rotation will not produce any change in your energies of the any rotational energy system. There is no change in rotational energy system with that kind of rotation. So about that axis, we will not be having any change in energy, even if you rotate. So that rotation is not possible. So because of that, we will not be having the third rotation, or the effect of third rotation is not there. So we have only 2 rotations which will affect the energy of the system. So for linear molecule, we'll be having total degree of freedom. Total degree of freedom will be equal to 3n minus 5, because 2 degrees of freedom associated with the rotational motion and 3 degrees of freedom associated with the translation. So for linear molecule, it will be degree of freedom will be 3n minus 5. Okay. So now if you consider a molecule, so if you consider again, consider molecule with n atoms. So if you are considering an acyclic molecule, so in that case, if you are having n atoms, then there will be n minus 1 bonds. This is the minimum. N minus 1 bonds will be. So if you are having n minus 1 bonds, there will be n minus 1 bond stretching. Bond stretching vibrations. So if you are having n minus bonds, then there will be n minus bond stretching vibrations will be. Okay, and the remaining two n minus 5 in the case of nonlinear, or 2n minus 4 is in the case of linear, gives this gives bending motions. So in this case, we have if you are having n atoms, if you are considering a cyclic molecule, if you are having n atoms, there will be at least n minus 1 bonds. If you are having n minus 1 bonds, there will be at least n minus 1 bond stretching vibration. So bond stretching vibration, number of bonds stretching will be n minus 1. So from this 3n minus 6 and 3n minus 5, we have to subtract this n minus 1. Okay? That is stretching mode of vibration. And then the remaining 2n minus 5, 1n minus 1 is gone. So 2n minus 5 will be the remaining number for the case of nonlinear case, remaining degrees of freedom, number of degrees of freedom. And in the case of linear case, it will be 2n minus 4, 1n minus 1 is uh, taken for this stretching vibrations. So remaining 2n minus 5 number of vibrations, or 2n minus 4 number of vibrations, will be associated with the bending motion. Okay? So first n minus 1 will be associated with the stretching vibration, and the remaining 2n minus 5 and 2n minus 4, for the case of nonlinear and respectively, that will be associated with the bending mode of vibration. And we will discuss the vibrations, stretching and bending modes with examples. Before that, we have, for example, if you are considering linear molecule, a linear molecule like carbon monoxide. So in the case of linear molecule, we'll let's say this is a linear diatomic molecule. Diatomic molecule. For diatomic molecule, n will be equal to 2 number of atoms. that molecule is equal to 2. So for linear case, the degree of freedom will be equal to 3n minus 5, 3n minus 5 for linear case. So this will be equal to 3 into 2 minus 5 will be 1. So only one particular motion or the vibration is possible in the case of linear molecule. Okay, vibrations. Okay, only one particular vibration, or we call this as a fundamental vibration. Okay, so only one fundamental vibration is possible. This is the fundamental vibration. Why it is fundamental means it is associated with the stretching and bending modes. We are not considering these overtones or the hot bands, all those vibrations that we are not considering now. So this is only fundamental vibration that we will get by using this. So that is the case. For example, if you are considering water, okay. So if you are considering H2O, H2O is a non-linear molecule. It's a non-linear molecule. You know that the molecule will be having a shape like this. This bend shape with some 104 degree of angle. So this molecule is not linear, which is a non-linear molecule. In this case, we'll be having n equal to 3, 2 hydrogen and 1 oxygen. So degree of freedom, total degree of freedom will be equal to 3n minus 6. Okay, because non-linear case it will be 3n minus 6. So this will be equal to 3 into 3 minus 3, sorry, minus 6. So this will give you 3 degrees of freedom, which means that it is having three fundamental fundamental mode of vibration. Or this is also called as normal mode of vibration. That is nothing but a fundamental mode of vibration or normal mode of vibration, which means that we are considering only that stretching and bending in the normal case, okay? Normal degrees of freedom, normal vibrational case. We are not considering the hot bands, the overtones, all those things. That cannot be discussed by using this equation. Okay, that's why it is called as fundamental mode or normal modes. So these are the normal modes or fundamental modes of vibration associated with the water molecule. There can be overtones, there can be other type of vibrations also possible. These are the fundamental mode of vibration or normal modes of vibration associated with the water molecule. So the water molecule can vibrate in three ways in fundamental mode of vibration. Okay. So that we can show in this figure. Yeah. If we consider the water molecule, it will be having this shape, and it is having a C2 axis. C2 axis means that if you are rotating this particular molecule like this, you are rotating like this, so it will come back at its hydrogen position to the original position after second rotation. So first this hydrogen will be going like this, and it will reach this position, and this hydrogen will reach into this position. Okay? So in that case, the water molecule is similar to that of the initial state. Again, if you rotate, the original hydrogen will come to its original position, that this hydrogen position, and this hydrogen will come to its original position. Okay? So within a single rotation, this molecule can be in the same state 2 times. Okay, that's why it is called as C2 axis. Okay? So if you are rotating it's 180 degree, it will be having uh, same kind of structure or same in the same physical form uh, when it is rotating with 180 degree, which means that with respect to that center axis, on both sides we'll be having hydrogen at the same position. Okay? When you are moving that with 180 degree, and again if you are moving with 180 degree, it will be having the same initial structure or initial position. And the about that C2 axis, we'll be having again the same hydrogens with the same distance and same angle. So with respect to that axis, these two hydrogens are in the same symmetric to each other. So that's why it is called a C2 axis. We can have two positions or two modes. When it is 180, when it is 360, we'll be having the same kind of structure for this hydrogen, this water molecule. About that axis, the hydrogen will be displaced in the same position. Or we can say that the hydrogen will be symmetric about that particular axis. So that's why it is called as C2 axis. We can have the same kind of structure two times with a single rotation. Okay, now if you are considering the modes of vibrations, then we have three different modes of vibration. We already discussed the three fundamental modes of vibration. And here we have oxygen. This hydrogen can go in this direction. So hydrogens go in this direction. And this particular vibration is called as symmetric stretching. So your oxygen will be here, and the hydrogen will be going in this direction. So this is called as symmetric. So in the next position, next time, okay, we will show in the figure. So this is the symmetric stretching, and this is bending mode vibration, symmetric bending. So the hydrogen will be moving like this about this oxygen position. So the angle will change. So in this case, in this particular symmetric bending case, angle is going to change. The bond length will be fixed. But in the stretching case, you can see in the stretching case, this bond length is going to change. This length is going to change in each time. But in the case of bending, this angle is going to change because this hydrogen moves here, this hydrogen moves here, so it will be moving in this position. So the angle is going to change into this. So in this particular case, angle is going to change, but the bond length will be same. Bond length will be same. And the third case is that antisymmetric stretching. So it is a stretching mode, which means that bond length is going to change. So this hydrogen is moving like this. So the bond length is increased, and then it will come back also. This hydrogen moves in the opposite direction. So that's why it is called as antisymmetric stretching. One hydrogen goes away from the oxygen, and the next hydrogen comes towards the oxygen. Then it is called as antisymmetric stretching. If both hydrogen are going away from the oxygen and coming back, means that coming towards the oxygen at the same time, then it is called as symmetric stretching. Okay, so all the atoms are going or vibrating same modes in the same frequency, then it is symmetric. Okay, if the atoms are vibrating in different frequencies, for example, in this case, this hydrogen is going away from the oxygen, and this hydrogen is coming towards the oxygen. In that case, the corresponding vibration is antisymmetric. Okay. And similarly, in this case, both hydrogen are going away from the oxygen with same angles. Okay, that's why it is called as symmetric stretching. And this symmetric stretching is having 3651 centimeters. That is the wave number position of this particular symmetric stretching vibration. And symmetric bending vibration is having 1595 centimeter inverse of wave number. And this is having 3755 centimeter. And also remember that the symmetric stretching we denote by mu1. So this one is mu1, and this one is mu2. That is the symmetric bending. This one is mu3. This is the antisymmetric stretching. And this one is perpendicular to that axis. Vibration is perpendicular to that axis. And this one is parallel. This one is also parallel. And if you want to go to the details of these vibrational modes and the corresponding change in the dipole moment, because when you are considering infrared spectroscopy, there should be an associated change in dipole moment. Otherwise, it will not be infrared active. So that is the basic condition for a molecule to be infrared active. There should be a dipole change by the infrared waves. So in this case, for example, if you consider this mu1, that is the symmetric stretching vibration of the water molecule. So this is the distorted molecule. This is normal molecule, and this is distorted molecule. Okay? So this is a normal molecule. When you are having symmetric stretching, your hydrogen will move away from this oxygen first position. So this bond length will be increased from when you are considering this normal molecule. Bond length will get increased because of the stretching. Oxygen from the oxygen, hydrogen moves away from oxygen. So like this. So the bond length will be getting increased. When the bond length is getting increased, here we have the dipole moment, which is getting. Also, when you are considering this distorted molecule, which means that the hydrogen moving towards the oxygen, okay, and the bond length will get reduced, and in that particular case, the total dipole moment will get reduced in strength. Direction will be the same. I'm not going to discuss all the details about the dipole moment. I will just say how we can calculate this dipole moment here. So if you are considering this stretching mode, there will be many videos associated with dipole moment. So if you are considering this particular water molecule, then dipole moment, if you want to calculate, it will be associated with the charge associated with this particular molecule and the distance separation between those charges. So if you are considering this oxygen, there will be two unpaired electrons, two pairs of unpaired electrons. Like these are lone pairs. They are unpaired electrons. So this electron and hydrogen charge. So electron, one electron will be distributed, will be shared. So that electron we have to consider. Okay. Then if you consider the dipole moment in this axis, so in these two axes, this two dipole moment will get cancelled. Okay. If you are considering the resultant dipole moment, you have to resolve this dipole moment, and these two will be having these components, sign components will be cancelling each other because they will be having same strength in and opposite direction. Okay, so these two will get cancelled. Only this component, cos component, perpendicular component, okay, only this component will remain, and resultant of this we are noting. Okay, this actually this will come like that dipole moment will come 2 into that charge 1.6 into 10 plus 9 coulomb, and this times the separation between this oxygen and hydrogen, that will be around 95.8 micro. So this times cos theta will come. cause of single this angle, if you consider that will be some 52.2 degree. And along with this, we have some ionic constants. Also, we have to consider 35% of ionicity of the hydrogen for this atomic. So this is the expression. This is normal expression with the Q into separation between the charges. This 2 will come from 2 oxygen and hydrogen pair. Okay, so we have to consider 2 times of that. So this is how we'll calculate this dipole moment, but you don't have to go into detail these things. So just understand that this dipole moment will increase when you are having this stretching, and dipole moment will get reduced when the hydrogen come close to this oxygen. And this is the normal dipole moment, normal position. So with this is a symmetric stretching. And similarly, if you consider bending, so this is the angle with 104 degree around 4.4. So this is the normal molecule, and with the bending, this hydrogen moves away from that. Then this hydrogen also moves away from oxygen symmetrically. That's why it is called a symmetric bending, and the dipole moment will get reduced because your angle is increased here, and if you take that cos of that angle, that will be less than this, the original one. Okay, so your dipole moment will get reduced here. Okay, and with 104 we have 52.2, and your dipole moment will get increased here. Here also again it will be getting, because your angle is coming very close to 0 here. It's coming to, will get increased. And when you are going from away, because this one will be having like 52 degree, right? So this is approaching when you are this angle is increasing, which means that it is approaching towards 90 degree. It is approaching towards 90 degree or cos 90. Okay, this time cos 90 will become 0 here. So your dipole moment is approaching towards minimum value. Okay, so when your angle is increasing between these hydrogen bonds, your cos theta is approaching towards 0, so that your magnitude of this dipole moment will get reduced. And when you are having 104, the magnitude is increased, and when you are having very small angle, it is large dipole moment. And in the third case, we have asymmetric stretching, and we'll be having a complicated dipole moment because we have to consider the direction also. So we have oxygen, this hydrogen, which is in this position, which is not going anywhere. We don't like to say, but this hydrogen is moving towards the oxygen, and this is normal position, and this is again this hydrogen is in the normal position, and this hydrogen moving towards the oxygen. So that is one hydrogen. Only one hydrogen is vibrating, and it is one bond is getting reduced, the other bond is fixed. So such kind of vibration is antisymmetric vibration, because which is the vibration is not symmetric with respect to the axis. How we can say that? If you are considering that central axis, the C2 axis, you will be having hydrogen position here, and the next hydrogen position here. So if you rotate this with 180 degree, then we will be having this hydrogen position here, and this hydrogen here. So they are not symmetric. With respect to that axis, this is not symmetric. That's why it is called as antisymmetric vibration, because with respect to this axis, this position of this hydrogen is not in the same position. With if you are rotating that with 180. So if you are rotating it 180 degree, we will have different position for this hydrogen. So this is not symmetric vibration. But in the case of asymmetric stretching, if you are considering, so for that case, for example, if your hydrogen is this position, and again this hydrogen is also in this position, and if you are looking about this axis, these two hydrogens are in the same at the same distance, or symmetric with respect to this axis. And also, if you are considering this hydrogen, oxygen, when that is symmetric stretching, when it is going to cross to this oxygen, okay, that case also, if you are considering the central axis, these two hydrogen will be symmetric to that axis, because this separation distance is same. So that's why it is called as symmetric stretching. Similarly, in this case also, bending mode also, we can say that with respect to that T2 axis, we'll be having hydrogen at the same position. Both hydrogen will be symmetric with respect to that axis. But in this case, it is not symmetric with respect to that axis. That is why it is called as antisymmetric. Okay. And the exact spectra that we will get from higher spectroscopy of the water molecule is looking like this. So from this, we can see there is an absorption peak at those vibrational frequency that we discussed. You can see this asymmetric stretching vibration at 3,700. This dip we are seeing, and this dip is associated with the symmetric stretching at 3,607, and this particular dip is associated with the asymmetric bending. So this is the exact spectra that we will get from a higher spectroscopy of water. So we will be having water here is an infrared spectra. Observe what are the infrared spectra out from that particular sample. Then you get that. So we have different peaks corresponding to each of these fundamental vibration. And you can also have some different other peaks so that you become your combination of vibration associated with this one. Now we will discuss the case, another example of the polyatomic case, that is the carbon dioxide. So for the case of carbon dioxide molecule, we have two different axes in this case. So one is that C2 axis that we already discussed in the for the case of H2O. That is the same, because with respect to this axis also, if we are rotating this molecule, then we can have the same kind of structure or same position for the height. So if you are moving this to this side and this to this that axis like this, we can have same kind of structure for the molecule two times, which means that if you are rotating that 180 degree, the first oxygen, let's say this is the first oxygen, this first oxygen will come to the second oxygen position, and the second oxygen will go to the first oxygen position, and the total molecule will be having same structure with respect to that axis. So two times same structure can be kept with respect to that axis. That's why it's called a C2 axis. That is, with respect to that C2 axis, the molecule is symmetric. And then we have another axis, the infinite axis. The infinite axis is nothing but the molecular axis which is passing through this bond line. And with respect to that axis, we can have infinite number of configurations. That's why it is called as the infinite axis. The infinite fold, this is infinite fold. Since rotation of the molecule about this bond axis to any angle, that gives identical axis. So if you are considering any rotation with respect to this this angle. Okay, that will be identical to this molecule. This molecule will be same. What in any axis, sorry, any angle, if you are rotating with respect to this angle, the molecule will be same. That's why it is called as C infinite axis, because it is infinite fold. Why it is called as infinite fold? Because uh, since rotation about this the bond axis through any angle gives identical aspects. Identical means that the same structure. And if you are considering the vibrations, we have for carbon dioxide molecule, we will be having this is a linear molecule, linear polyatomic molecule, linear polyatomic molecule. So we have to consider the equation total degree of freedom, or we can say the number of fundamental modes. Number of fundamental mode of vibration, that will be equal to 3n minus, for linear case it is 5. So we have n equal to 3. So that is 9 minus 5 equal to 4. So we will be having 4 modes of vibration. But in the figure we can see that only 3 modes of vibrations are available. So the fourth mode is also associated with this bending mode of vibration. Because this mu2, or the bending mode of vibration, is not only in this screen or in this paper, also it will be coming out of the plate. I will discuss that after discussing this one. So there are basically 4 modes are available for carbon dioxide. Using this equation, 4 fundamental mode of vibrations are possible. First one is symmetric stretching, as we discussed before. So this oxygen moves away and coming back to this position. So this carbon dioxide will be having like this for symmetric stretching. Then we have original position, and then can go away. And this is called as symmetric stretching. Okay? So oxygen is coming towards this carbon dioxide, normal position. So this is the symmetric stretching, and it is happening at 1,330 centimeters, and it is called as the mu1 frequency. And this is mu3 because it is antisymmetric. That is mu3, and this is at 2,340. In this case, only one oxygen going towards carbon, carbon going towards this oxygen, and this one is fixed. So in this case, this oxygen will be going towards carbon, and this is normal position. And then this oxygen carbon is. So this is asymmetric stretching because only one side it is increasing and the other side it is one. Okay. So this is asymmetric stretching, and the bending mode. In the bending mode, this two oxygen going up in the screen and this carbon going down. So this will be like carbon coming here, oxygen going up. Okay. Then this is the normal position. Then this oxygen coming down. So this this is the bending mode of vibration. The angle between this bond will change in each case. So that is the bending mode. It will happen at 607. We also need one more mode of vibration because by theoretical calculation we get 4 modes of vibrations. So in this bending mode we have another mode with the same energy, same frequency, everything same. That's why we call this particular mode as this bending mode as degenerate. This mode is degenerate because there are two different kind of vibration with same energy, but different in different direction. Okay? So this one is in this screen, and this one come out of the screen. So it will come out of the screen like this. Draw it. So it is coming out of the screen, and it is going into the screen. Okay? Also, it is going into the screen like this. So in that case, the oxygen position will be like this, into the screen, and out of the screen it will be coming. So this time also the angle will be. So this is another mode which is also a bending mode with the same energy, same frequency, same spectral position at 667.3 centimeters, but in a different direction. So the mode of vibration is different, but energy is same. That's why it is called as a degenerate state or degenerate vibration. So with this mode also, into and out of the plane, into and out of the screen, we have total number of vibration, fundamental vibrations, which is for the case of carbon